This video is about the growth rate of a function and what that has to do with the convergence or divergence of series. So our main question is, given a series an of positive terms, does that series converge or diverge? For this video, you will need to know what a series is and what it means for a series an to converge or diverge. But you don't need to know any particular tests for convergence or divergence yet. This video is about intuition rather than rigorous series tests. Series tests are important, but they are most useful when connected to intuition. Often, students think of series tests as being just a big list of things to try for series, and they tend to struggle with the intuitive side of deciding whether a series looks like it should converge or not based on what the terms look like. So in this video, we're hoping to develop that intuition so that the series tests can actually verify what you already sense about a series. So our first step is to establish some general things to keep in mind about series. First of all, convergence or divergence is what I like to call an eventually property. In other words, it has to do with what happens to the partial sums as n goes to infinity, not what happens to the terms at the beginning. So the first finitely many terms don't matter. So in particular, the terms of the series might be positive, negative, all over the place for finitely many terms. But as long as they are all positive from some point on, then the topics I'm going to discuss in this video are going to be relevant. If you've heard of conditional convergence versus absolute convergence, we won't need to talk about that distinction in this video because as long as the terms are all positive from some point on, conditional convergence is not possible. Because the absolute value of a positive number is just that number, the absolute value won't do anything. So all of our series in this video will either converge absolutely or they will diverge. So here is one of our main intuition principles. In order for the series an to converge, the terms must be small, i.e. close to zero, and trending smaller. We cannot get a finite sum by adding infinitely many big terms. So as a couple quick examples, if an was n squared, then we would definitely get an infinite sum because we'd be adding up 1 plus 4 plus 9 plus 16 plus and so on. That's definitely infinite. And in example 2, even if an is 1, the sum of 1 plus 1 plus 1 plus 1 plus and so on forever and ever, that's also going to be infinite. If you've studied the divergence test, this is what the divergence test says. If the limit as n goes to infinity of an is not 0, then the series diverges. So the divergence test makes rigorous this intuitive idea that in order to converge, the terms of the series must be getting closer and closer to 0 rapidly. But you might have already learned, and you can see the divergence test does not say the converse, which is if the terms do go to 0, that's not enough for the series to converge. So we need some more intuition. So intuition item number 2, functions that grow faster as n goes to infinity win over functions that grow slower. Now what do we mean by that? If an looks like a fraction, and often the examples that you'll see in Calculus 2 do have this form, So if an looks like f of n over g of n, then as n gets big, if f of n grows faster than g of n, then the series is going to diverge, because the fraction f of n over g of n is going to just keep getting bigger. Now, if f of n is less than g of n, as n gets big, then the series might converge if g of n grows fast enough compared to f of n. If you've studied the p-series test, that gives you an example of why we cannot just rely on f of n being less than g of n to determine that the series converges. It turns out that the series 1 over n to the p converges when p is bigger than 1, but diverges when p is less than or equal to 1. So what do we mean by fast enough? Let's get a feel for how fast g of n grows compared to f of n. We're going to use big O notation, and if you've studied computer science, you may be familiar with this. But we're going to use it to try to compare the growth rates of f of n versus g of n, so we can decide whether g of n is growing fast enough compared to f of n in order for the series f of n over g of n to converge. Big O comes from the word order. So the order of a function is a measure of how fast a function grows as n gets big. So when we say big O of f of n equals big O of g of n, that means that f of n and g of n are comparable in their growth rates. Now there's some technical details if you want to read them, but essentially it means that f of n and g of n are comparable in their growth rates. When we say that big O of f of n is less than big O of g of n, that means that g of n grows faster than f of n in some sense. So let's look at a couple of examples to try to get a feel for big O. Big O of 1 is less than big O of n. We know that 1 is less than or equal to n for all n greater than or equal to 1 if we compare the function 1. And notice I'm just drawing dots because we are thinking about series where the function's only defined for positive integers. So the function 1 is constant, whereas the function n keeps growing. There is no way that we can get n to be less than or equal to a constant times 1 for all n. So big O of n is bigger than big O of 1. In our next example, O of n is equal to O of 5n. So notice that it's not enough just for 5n to be bigger than n. N and 5n are comparable because 5n is less than or equal to 5 times n for all n greater than or equal to 1. Okay, so having seen a couple of these examples, let's go over the rules of big O. Example 2 showed that big O is not affected by constants. So big O of a constant times f of n is the same as big O of f of n. As another example, big O of 7 times square root of n is big O of square root of n. Next, the dominant term in a function, which is the one with the biggest big O, actually determines big O. So big O of n squared plus n is big O of n squared, because n squared is dominant over n. Likewise, in example 7, The biggest power of n that we see is n to the 3/2. So big O of 8n to the 2/3 plus 5n to the 3/2 minus the square root of n plus 1/2 is big O of 5n to the 3/2. And because constants don't matter, this is big O of n to the 3/2. So now let's get into what big O can tell us about series. If big O of f of n is greater than or equal to big O of g of n, then the limit as n goes to infinity of f of n over g of n is not going to be 0. So the series f of n over g of n is going to diverge. In example 8, we have the series 4n cubed minus n squared plus 8 all over 6n squared plus 7. Big O of the numerator is big O of n cubed, because that's the dominant term and constants don't matter. That's bigger than big O of n squared, which is big O of the denominator. So we find that big O of the numerator is bigger than big O of the denominator. So the series diverges. Now here's what we alluded to earlier. If big O of f of n is less than big O of g of n, then the series might or might not converge. So using the examples from a previous slide when we mentioned the p-series test, it turns out that the series 1 over n diverges. But the series 1 over n squared converges. And you'll learn that when you learn the p-series test. So we can see that n squared grows fast enough compared to 1 that the series 1 over n squared converges. But n itself does not grow fast enough compared to 1 for the series 1 over n to converge. The series 1 over n diverges. Okay, so what do we mean by sufficiently larger? I'm going to introduce a notation that will help us discuss what we mean by sufficiently larger. We will write this symbol that looks like two less than symbols right next to each other. And we will read this out loud as that big O of g of n is sufficiently larger than big O of f of n, enough for the series f of n over g of n to converge. Or equivalently, if we want to have something that we can read left to right, we will also read this expression as big O of f of n is sufficiently smaller than big O of g of n. Again, we mean sufficiently smaller for the series f of n over g of n to converge. So going back to the graph that we saw in the first slide, we can see that for the first finitely many terms, these functions may cross over each other. One of them might be greater than the other at first, but then the other one will start to take over. But eventually, from some point on, these functions all seem to have an order, where one function is clearly going to grow faster than another in this order. So we might guess from the graph, the growth rate of n is the smallest one here, followed by n squared, followed by 2 to the n, followed by n factorial, followed by n to the n. So is it true that all of these have sufficiently greater order than the previous one in order for the series of one over the other to converge? Well, not quite. So even though big O of n is less than big O of n squared, it's not true that big O of n is sufficiently smaller than big O of n squared to make a series whose dominant term is n on the top and n squared on the bottom converge. So let's explore more about that. So here are some rules about sufficiently less than that you can prove with series tests, and as you proceed through your calculus course, you will learn tests that will verify all of these rules that I'm going to give you. So first, for power functions, big O of n to the p is sufficiently less than big O of n to the q if and only if q and p differ by more than 1. So you'll use the p-series test and the limit comparison test to verify this fact. But let's look at an example. This is example 10 again. an equals 1 over n squared. So big O of 1 is big O of n to the 0, because n to the 0 is 1. And according to our rule, this is sufficiently less than big O of n squared, since 2 minus 0 is 2, which is strictly larger than 1. So the series an converges. On the other hand, in this example, we have an equals 3n over 4n squared minus 1. For the rest of the examples in this video, I encourage you to pause the video and see if you can work out the answer for yourself before continuing. So pause the video and try to decide based on this rule about sufficiently less than whether the series an in example 11 converges or diverges. Okay, so big O of n is not sufficiently less than big O of n squared because 2 minus 1 is 1, which is not strictly greater than 1. So the series diverges. Example 12, an equals 5n to the 8/7 minus 4n to the 1/5 plus 2, all over 7n to the 4 plus 3n minus the square root of n. Does this series converge or diverge? The dominant power on the top is n to the 8/7. The dominant power on the bottom is n to the 4 when we're ignoring constants for the purposes of big O. So big O of the numerator is sufficiently less than big O of the denominator, since 4 minus 8/7 is 20 over 7, which is strictly larger than 1. So the series converges. Next, we're going to talk about exponential functions. Note that this is a function where there's a constant in the base and n is in the exponent. So as long as we're talking about growth exponential functions where the base is bigger than 1, then an exponential function with a bigger base is going to grow sufficiently larger than an exponential function with a smaller base. You can use the geometric series test or the limit comparison test to see this. So example 13, take a look at an equals 2 to the n plus 72 over 5 to the n minus 8. Does the series an converge or diverge? Okay, so big O of the numerator is big O of 2 to the n, which is sufficiently less than big O of 5 to the n, since the base 5 is bigger than the base 2. So the series converges. A small note here that if you have the same base, but you increase the power, that will not affect big O. For example, if you have b to the n plus 1, that's the same thing as b times b to the n. So that's a constant times b to the n, and constants don't matter. So big O of b to the n plus 1 is big O of b to the n. So in example 14, we have an equals 2 to the n over 2 to the n plus 3 plus 5. We can see that big O of the numerator is actually big O of the denominator. 2 to the n plus 3 is 2 to the n times 8. And 8 is a constant. And so the series is going to diverge, because as n gets large, we're going to be adding terms that are getting closer and closer and closer to 1/8. In other words, 1 over 2 cubed. The limit as n goes to infinity of an is 1/8. So not 0. So the series is going to diverge. Next, exponential functions always win over power functions. Big O of a power function is always going to be sufficiently less than big O of an exponential function, as long as the power is greater than or equal to 0 and the base b is greater than 1. So for example 15, an equals 7n to the 31 over 4 to the n minus 8n plus 1. Okay, so big O of n to the 31 is sufficiently less than big O of 4 to the n, because n to the 31 is a power function and 4 to the n is an exponential function. So the series converges. And finally, a few more functions that you will see frequently in a typical Calculus 2 course concerning series. Exponential functions always lose to factorials, and factorials always lose to n to the n. When you learn the ratio test, you can verify each of these facts as well. So example 16, an equals 6 to the n minus 1 over n factorial. Big O of the numerator is big O of 6 to the n, which is sufficiently less than big O of n factorial. So the series converges. Example 17, an equals n to the n minus n squared plus 1 all over n factorial plus 85. Now note that we have n to the n on the top and n factorial on the bottom. So this series diverges because n to the n grows faster than n factorial. In summary, given a series an of positive terms, or at least positive from some point on, where an is of the form f of n over g of n, if big O of f of n is greater than or equal to big O of g of n, then the series diverges. If big O of f of n is sufficiently smaller than big O of g of n, then the series will converge. In order to calculate big O, we learned that constants do not affect big O, and the most dominant term of a function determines the big O. We learned that for power functions, big O of n to the p is sufficiently smaller than big O of n to the q if and only if q minus p is strictly greater than 1. We learned that big O of b to the n is sufficiently smaller than big O of c to the n if and only if b and c are bigger than 1 and b is less than c. And finally, big O of n to the p is sufficiently smaller than big O of b to the n, which is sufficiently smaller than big O of n factorial, which in turn is sufficiently smaller than big O of n to the n. You can use series tests to verify and confirm each of these facts. I hope you found this video helpful.